Hi, everybody. My name is Abigail Circelli. I work with, please call me Abby, by the way. I work with Dr. Clark. We are a fundamental electrocatalysis lab here at Penn State, and I'm really excited to talk about my research today, so thank you so much for the opportunity. I'm going to be talking about elucidating the origins of electrocatalytic phenomena using steady-state isotopic transient kinetic analysis. So, as I'm sure we're all aware, major concerns have been expressed regarding the security of our energy future. Therefore, we must develop alternative approaches in order to produce commodity fuels and chemicals. And a prospective approach of this is to implement electrochemical conversion processes that have the ability to form high-value products, such as ethylene and ammonia. And this can be achieved through electrocatalysis, where we drive chemical transformations via electricity. However, a lot of electrocatalysts suffer with inadequate rates of reaction or activity. They suffer really poor activity. And there are generally two catalytic developmental design strategies in order to increase this type of activity. The first and more common one is to increase the number of active sites, right? So you're increasing your loading, you're increasing your electrochemically active surface area, you're increasing the number of active sites on exposed to the reaction site. And in theory, this is a great practice, right? Because if you increase the number of active sites, you're increasing the performance of your catalyst. But in practice, that's not necessarily true because you have a lot of mass transport limitations when you overload your catalyst, essentially. And then there's another design strategy known as, where to increase your activity, where you can increase the intrinsic activity of each active site on your catalyst. And what does that really look like? What does that actually mean for electrocatalytic phenomena? So generally, there are two reports of catalytic activity in literature. The first is an apparent activity, and this is a product generation rate normalized by something like a geometric area. And this is a great report for comparing catalysts across different research groups, and to understand general performance of the cell itself. But actually understanding fundamental origins via this apparent activity report is not very ideal. And because you're not understanding the structure of the surface by any means when you report it as apparent activity. However, intrinsic activity is a more formal definition of activity where you can understand the activity on a per site basis, and this is really important into understanding the fundamental origins of enhancing or inhibiting catalytic activity. In this case, we have intrinsic activity, or a site time yield for a particular product. It is equal to the product generation rate normalized by the electrochemically active surface area, or your ECSA. And this measurement, the ECSA is usually significantly larger than your geometric area because it takes into consideration the nanostructuring of your electrocatalyst itself. But a more informative definition of intrinsic activity, or the site time yield, is the ratio between intermediate surface coverages leading towards a particular product by the surface lifetimes, or how long those intermediates are actually on the surface for. And this is the only definition that actually provides insights into these activity origins, understanding which parameter of activity, because activity is a function of two key parameters. It's a function of coverage and lifetime. So this is the only definition that actually allows us to understand which parameter is inhibiting or enhancing the activity over a catalytic surface. So since these two parameters are so important in understanding activity, we want to develop ways in order to measure these type of parameters. And intermediate surface coverages have been investigated in electrocatalysis through a variety of analytical techniques. The first one I would like to discuss today, this is a brief literature overview of people in literature obtaining surface coverages via a variety of techniques. So this is a technique known as radioactive labeling, where essentially, and essentially you can monitor the surface in order to understand what's absorbed onto it. But essentially, your reactant is a radioisotope. So in this example, this is a C14 labeled methanol. And then, this reactant will essentially adsorb to the surface, and these radioisotopes actually emit what's known as a soft beta emission. And this soft beta emission is, I'm talking in air here. Okay. Sorry. And then these beta emissions are detected by a scintillator, essentially. So this is the working electrode, and this is where your detector is, essentially. And this is a positive technique for the fact that you can study adsorbed species on a surface, but there are many downfalls, we believe, to this type of technique. First of all, this is the use of a radioisotope, which is very expensive and very dangerous. And it's not really this is not necessarily a common practice experiment that people can just go into the lab and do because you're using, radioactive material. And also, it's not exactly clear how one can identify the number of unique surface intermediates on the site. So telling the difference between a poison or something that's actually leading towards the production of something else it's not clear how they actually differentiate between those type of things. So you can really only see the intermediates that are carbon labeled 14, essentially. And then also, these beta emissions, these soft beta rays, both emit in the bulk and at the surface of the electrode. And so therefore, the electrode has to be thick enough in order for the bulk signal to not overwhelm the detector, essentially. And in this paper, they actually had a platinum deposition of about 100 microns, which is actually incredibly thick, relatively very thick, and in which we would assume that there's a lot of mass transfer issues corresponding to this type of very thick platinum deposition. So although this is a technique to relatively understand the coverages of absorbed intermediates, it's not necessarily the best approach, we believe. And then another approach, another analytical technique is FTIR. This is a fantastic technique that allows us to understand intermediate coverages for a variety of electrocatalytic reactions. I'm definitely not an IR person, and I don't think any of us here are because we are mass spec people. But essentially, this is a great technique to understand, not only to understand what's on the surface, but actually identify what is there and its relative abundance, essentially. So it's generally very quantitative, and from the literature that I have read on FTIR, it is very challenging to actually calibrate and correlate these integrated band intensities to a specific coverage of reaction intermediates. We actually have a student in our lab, Danny, she's right there, who is going to be working on something such as this. And then in thermal heterogeneous catalysis, there is an in situ analytical technique which measures the number of surface intermediates and their corresponding surface lifetimes. And this technique is known as steady state isotopic transient kinetic analysis, or SITKA. And SITKA is a steady state measurement. So before you actually do a SITKA experiment, steady state must be established and maintained. And once steady state is established, the inlet feed stream is rapidly switched to a feed stream that contains an isotopically labeled reactant species. And now as this inlet is now entering the mass spectrometer, it's replacing the original reactant on the catalyst, and you're this exhibits a transient change on the catalytic surface. And this, in the isotopic composition of the products in particular, which is kind of on the schematic over on the right-hand side here, essentially you can observe this transient change via a mass spectrometer. And then the integration of the transient response is directly proportional to the amount of surface intermediates leading towards that particular product at the moment of the switch. So then you can convert this these number of intermediates to a coverage. And then furthermore, you can also take your transient data and fit it to a complex exponential function known as a Sitka model. And these Sitka models can then give you the lifetimes of your reaction intermediates. And these Sitka models kind of represent the number of unique surface intermediates and their relationship with one another. And we will discuss the Sitka models later on in the presentation. But overall, this specific technique of measuring the coverages and the lifetimes of reaction intermediates has never been performed before in electrocatalytic systems due to the complications of product analyzation in an aqueous environment. And now these challenges can actually be alleviated through differential electrochemical mass spectrometry. I don't know who put Ezra and I back to back, but you've never seen this slide before. So let me talk to you about this slide. This is DEMS, where an electrochemical cell is coupled to a mass spectrometer via a prevaporation membrane. And this enables the real-time collection, quantification, and identification of volatile electrochemical reaction products. And over here, as you've seen already, this is a schematic of an electrolytic process where you're applying an energy to a system, or you're applying an energy to a catalyst, and in response you're obtaining some type of Faradaic response, which then also you can obtain this mass ion current response. So essentially you're doing electrochemistry and mass spectrometry simultaneously, which is a very powerful technique for electrochemists. So as Ezra mentioned earlier, the cell design is, or the performance of your cell is highly dependent on the cell configuration itself, right? So in this is a classic DEMS cell design, essentially, where the electrocatalyst is deposited directly onto the prevaporation membrane. This prevaporation membrane then interfaces the mass spectrometer, and this is the classic DEMS cell design, where essentially your collection efficiency of volatile species is maximized, and your product detection time is minimized, essentially, because of that, where the prevaporation membrane is relative to the catalyst itself. So this design was implemented by my advisor and studied by my advisor back in his grad studies, where they essentially took this DEMS technique of now this classic DEMS cell design and compared it to conventional analytical methods like sampling in a headspace and sending that effluent to AGC. And you can see, as you've seen earlier, that the data corresponds excellent with one another. Just however, the DEMS approach was actually acquired roughly 2 orders of magnitude faster. So this just validates the accuracy of this DEMS configuration, and that it validates the fact that this is an appropriate setup. Furthermore, they also wanted to understand product quantification as a function of scan rate. And as you've seen earlier, we can go up to, or Ezra and his team scanned the potential at 100 millivolts per second, and they got accurate product quantification. So not only is this the cell configuration fantastic for something like electrochemical Sitka, but it also allows this rapid analyzation, which is exactly what is needed. And as you can see, now this setup and this classic DEMS cell design is the foundation of our electrochemical Sitka approach. So in order to perform electrochemical Sitka, a custom reactor and a custom reactor setup has to have been built in order to enable these fast, rapid switches of electrolyte and reactant and what have you. So the first thing I'd like to just point out is the classic DEMS cell design, where that catalyst is deposited directly onto the prevaporation membrane. We sputter coat, and this is just a very high surface area platinum electrode that I will discuss in a little bit later. But we have our electrocatalyst is sputter coated directly onto that prevaporation membrane, which then interfaces our mass spectrometer. And then coupled to this reactor is a reactor setup that enables the rapid switching of electrolyte from something like C12 labeled methanol to something like C13 labeled methanol using a peristaltic pump and a switch valve. And we also included a purge valve in order to eliminate mixing of the electrolytes. And if you're coming onto the lab tour today, you will see the setup in real person and in real life, and hopefully you can gain a better appreciation for what went into actually designing something such as this. Okay, so now that we have built a reactor and a reactor setup, now we need a reaction in order to validate our electrochemical Sitka approach. So there was a lot of criteria that went into consideration when considering an electrocatalytic reaction to choose. The first thing is that this is an isotopically labeled experiment. Therefore, our reactant could not exhibit a kinetic isotope effect. We also wanted to make sure that there was a relatively minimal signal overlap, just because this is a validation reaction, and we wanted to make sure that the product of interest that we were analyzing didn't have too much deconvolution to deal with. We also wanted to ensure that, which is really probably the main reason why we chose this reaction, is that we wanted to choose a reaction that allowed us to use a catalyst that has multiple measurements or multiple methods of measuring the electrochemically active surface area. Because we're acquiring a coverage, we definitely want multiple methods in order to validate the fact that our ECSA is accurate, is being calculated accurately. So therefore, we chose methanol oxidation over a platinum surface. Methanol oxidation undergoes a 6-proton and electron step to form the dominant product of CO2. And so methanol can adsorb to the surface and undergo a dual mechanistic pathway. So the primary pathway is through the formation of adsorbed CO. And the rate determining step of this pathway is adsorbed CO and the chemical coupling of a surface hydroxide to form a COOH intermediate, which is this guy right here, and then which can further oxidize to form the dominant product of CO2. Or it can undergo a secondary pathway. Sorry, guys. It can undergo a secondary pathway through the formation of soluble intermediates such as formaldehyde and formate. These can desorb and be final products, or continue to react, continue to oxidize on the surface to form the dominant product of CO2. So now I just, so that we can appreciate the methanol oxidation reaction over a platinum surface. This is methanol oxidation over a platinized platinum surface, so it's just a high surface area platinum electrode. I just want to quickly go over what the CV looks like and to understand the Faradaic processes that are going on over this platinum surface, both in a blank electrolyte and with methanol in solution. So we'll start with the blank electrolyte, which is just 0.5 molar sulfuric acid with at 50 millivolts per second. We'll start at roughly 0.3 volts versus RHE, and we're going to scan cathodic, or in this reverse direction. We see the onset of hydrogen. We see these 2 waves here, which is the onset of hydrogen onto different platinum facets. And then our cathodic vertex here is the onset of hydrogen evolution reaction, or HER. And then we're going to start to scan anodic, or positively, where we see hydrogen desorption from these platinum facets, and then this large non-Faradaic region here until roughly 0.75 volts versus RHE, where we see the onset of platinum oxidation, until our anodic vertex, which we see is oxygen evolution reaction, or OER. And then we can scan cathodic again, and we see the platinum reduction. And now, if we introduce 0.1 molar methanol into solution, we see a significant difference in our cyclic voltammogram. Where now HUPD is suppressed by roughly 50% because we have methanol dehydrogenation onto the platinum surface. And then at roughly 0.5 volts versus RHE, we see the onset of this wave here, known as the low potential methanol oxidation wave. It reaches a maxima, and then at these higher potentials, it actually decreases. And then we actually see another onset of methanol oxidation here, which is known as the high potential methanol oxidation wave, until we reach OER. And then we can reverse it, and we see platinum oxidation again with a reverse scan methanol oxidation as well. And now the goal of applying electrochemical Sitka to methanol oxidation is to understand the activity behavior of the low potential methanol oxidation wave. So why we want to answer the question for the coverages and the lifetimes, for the intermediates leading towards the production of CO2, why does this activity have a maxima and then at these higher potentials decrease? So this from 0.6 to 1 volt versus RHE is the potential range that we will be performing eSitka in. So now we want to ensure that because we're doing a mass spectrometry technique, we want to ensure that we get high signal. And as I mentioned earlier in the beginning of my talk, one way to increase the activity of your catalyst is to increase the surface area. And that's what we wanted to do to just maximize our signals as best we could. So what we decided to do was use an electrodeposition technique known as platinizing platinum to increase the surface area of our eSitka electrode. So we originally took a PTFE membrane and sputter coated about 100 nanometers of platinum onto that PTFE surface. And then we did an electrodeposition using a chloroplatonic acid solution, which essentially you're just applying a negative current to your 100 nanometers of platinum. And the platinum ions in solution are then depositing onto the surface, and you create a very high surface area electrode. Now, when you're doing this, you got to be really careful because you essentially need these pores in order to actually have a product detection, but you also want to increase your surface area as much as you can. So we went through a variety of experiments in order to ensure that our collection efficiency was still staying at 100%, which is just normalized by the collection efficiency that we were getting at 100 nanometers of platinum, and then as a function of platinum deposition time. And we saw that it was optimal where the collection efficiency was not suffering at roughly 6 minutes of platinum deposition. And this is our high surface area platinum electrode that we use for electrochemical Sitka. And so now we have that high surface area platinum. We want to actually quantify the electrochemically active surface area of this catalyst. And we use 3 different methods in order to do that. So the first method that we used is known as hydrogen under potential deposition. This might look familiar from the platinum CV that you saw on a previous slide, where essentially HUPD is when a monolayer of hydrogen forms on the surface at potentials positive of its Nernst reversible potential. So essentially you can integrate these waves here and use a specific charge density, a very common number found in literature, in order to calculate the ECSA. And we calculated an ECSA of 143 centimeters squared. And then the second technique we used was a universal technique known as capacitive cycling, where you can actually do CVs, truncated CVs, in the non-Faradaic region of your CV, and then essentially what you're doing is that when you can charge the double layer as a function of scan rate. So it's a direct correlation between the double layer charging and your scan rate. And essentially you obtain this curve, you obtain this slope, and then you can use the material-specific capacitance in order to obtain an ECSA. Now, this is a very universal technique that can be applied to any catalyst, but at the same time, it's probably the largest estimate just because specific capacitance of each material is different, and the accepted value is around 25 microfarads per centimeter squared, which is what we used here to calculate this 147 centimeter squared value. But obviously, this varies between catalysts, and so this is just a rough estimate, but it's another great way to estimate the surface area. And then our third and final method of quantification was CO stripping, where essentially you have saturated CO in solution, and you apply a potential to the catalyst, and you create 2/3 of a monolayer of CO on your surface, and then you remove CO from that electrolyte, and essentially you oxidize that CO off to CO2. And you can integrate this charge, and using a specific charge density found in literature, similar to the HUPD value, you can obtain an ECSA, which we obtained 151. So you can see that all 3 methods are in very good agreement with one another. So now that our ECSA is measured and our surface area is known, we need to actually calibrate species of interest and species that we actually want to detect and want to quantify. So Ezra has spoken about this for a little bit, so I don't want to, I apologize for the redundancy, but we can go through it again, and I hope that maybe we can gain a better appreciation for it. Okay, so really what this is doing is a chronopotentiometry staircase. So essentially you're applying a current to the catalyst, a fixed current to the catalyst, and obtaining a mass ion current response. And it's really important to understand that all the current that's being applied to that surface is going towards the production of the mass ion current that you're monitoring. So therefore, this is just this calibration was done in 0.5 molar sulfuric acid. So if we apply a negative current to our catalyst, the only we can assume and safely assume that all of the current that's being applied is going towards the production of hydrogen. That's why a calibration like this works for this particular species. So then we can take our the last 80% of our step, and for each step, and plot that against our known fixed current density in order to obtain a calibration slope. And then this calibration slope is then used when you actually are monitoring an M/C2 signal. You normalize that signal by your calibration slope in order to convert your mass ion current to partial current density. And the same procedure was done for oxygen. So now we're just applying a positive current to our catalyst, and the only product that's being produced in this environment is oxygen, and therefore we can again create this calibration slope in order to obtain partial current densities for oxygen production. So yes. And now we also wanted to calibrate the species of interest, which is carbon dioxide production. And we actually used a method known as CO stripping. So CO stripping is a powerful technique in electrochemistry because not only can it provide you an electrochemically active surface area, but you can also do CO2 calibration in this way as well. So essentially, as I mentioned, you just create this 2/3 of a monolayer, and then you want to oxidize that monolayer off while simultaneously monitoring the M/Z44 signal corresponding to the production of CO2. You can integrate the 44 signal and in the mass spectrometer, and you also integrate the strip from the electrochemistry in order to obtain a charge. And this is how we essentially calculated our calibration. And interestingly, so we know that the oxidation of CO to CO2 is a 2-proton electron step, but when we actually are going from methanol to CO2, it's a 6-proton electron step. So to account for the remaining electrons that are being transferred, we just multiplied our denominator by 3 and obtained a single point calibration for the production of CO2. So now that we have calibrated the species of interest, now we can actually understand these partial current densities and how much of this current response is actually going towards products that we're interested in. So on the left here we have our methanol oxidation over platinum, this is the electrochemistry, and this is the corresponding mass spectrometry, where we're monitoring mass ion currents 2, which is hydrogen, 31, which is the consumption of methanol, 32, which is the convolution of the consumption of methanol but the production of oxygen, and the M/Z44 signal, which corresponds to the production of hydrogen. And I didn't show how we deconvoluted the 32 signal here, but we have done that. We just used the mass spectrum, the fragmentation mass spectrum in order to do that. I'm sorry, I should have had a slide on that. But essentially, we were able to calculate the partial current densities for carbon dioxide, oxygen, and hydrogen using the calibration curves. And then from here, now we have these partial current densities. We can actually normalize them by our total current in order to obtain a Faradaic efficiency, or how much of that current is actually going towards the production of that species. And we can do this as a function of potential, which is really interesting to me. So now that we have calibrated our systems and calibrated the species of interest, we want to quantify our mass spectrometer response time. So really, we just wanted to see how fast the mass spec could actually detect electrochemistry. So essentially, we just applied a potential to the catalyst, and then we removed that potential and let it go to open circuit, and we were able to fit this transient response to an exponential function and obtain a constant lifetime as a function of potential at roughly 0.5 seconds. So this essentially means that any kinetics that are faster than 0.5 seconds, we wouldn't actually detect in this transient response. So this is sort of our detection limit for electrochemical measurements. So now we wanted to quantify our reactant switch time. So this is more of like valve dynamics, where we're switching from one electrolyte to another, and we had a concentration of methanol in one vessel and 0 concentration of methanol in the other, and we switched between the two as a function of flow rate, and again fit our transient response to a exponential function in order to obtain a reactant exchange time constant as a function of flow rate. And we see that at 200 milliliters per minute, we have an exchange time of roughly 0.8 seconds. So therefore, 200 milliliters a minute were used to perform electrochemical Sitka. Sorry. Okay, so now we can actually get into our experimental data, where we've done electrochemical Sitka for the first time over a platinized platinum electrode. So as I mentioned earlier, that we were investigating the low potential methanol oxidation regime from 0.6 to 1 volt versus RHE. So essentially we applied a voltage to the catalyst for a total of 10 minutes and introduced C13 labeled methanol for the first 5 minutes of the reaction, for the first 5 minutes of the experiment. And then at 5 minutes, we rapidly switched that electrolyte to an electrolyte containing C12 labeled methanol, and we were monitoring the corresponding 45 signal, which is C13 labeled carbon dioxide, and the 44 signal, which is C12 labeled carbon dioxide, and which we converted into these partial current densities using the calibration slope from the previous slides. Also, I do want to just note that you can see there really is no perturbation in the steady state measurements here. There is no disruption of steady state. So essentially, that's just a validation that steady state was not interrupted during our experiment. So now the first thing we wanted to do is quantify the steady state intermediate coverage. So we took that the transient decay of the 13 labeled CO2 response in the mass spectrometer, and we were able to integrate that, and using this equation down here, able to obtain steady state coverage of total reaction intermediates leading towards the production of CO2 as a function of potential. And you can see that the coverage of total reaction intermediates is quite high until roughly 0.8 volts versus RHE, where it actually starts to die off. And we can kind of correlate this type of trend to the coverages that we see of oxygen and hydroxide. So this coverage was actually obtained in a blank electrolyte, where we were just looking at the charge density of oxygenated species in a blank electrolyte, no methanol there. And this is just kind of to show you that these oxygenated species start to come on the surface at roughly 0.7 volts versus RHE, which kind of understands that these active sites are being taken up by oxygenated species, and therefore methanol is no longer being able to react onto the surface. So now that we've quantified the coverages, we can now take a look at the lifetimes. And as I mentioned earlier, the lifetimes are obtained through a complex exponential function known as a Sitka model. And these Sitka models represent the intermediates that are on the surface and their relationship with one another at the moment of the switch. So these models are considering irreversible adsorption and irreversible reaction kinetics. So this is so the first one is a single pool model, which essentially you just have a reactant going to one intermediate going to a product. This is your most elementary reaction. A serial pool model where you have intermediates leading towards another intermediate, which then produces a dominant product. And then you have a parallel pool model where you have two separate intermediates on the surface simultaneously leading towards the same product. And what we did through a minimization of variance technique was fit our data to all three models, and you can see that our data aligns exceptionally well with the parallel pool model. And this also corroborates with our mechanistic understanding of the methanol oxidation reaction, which undergoes a dual mechanistic pathway. So this is the parallel pool model that we used to model our transient decay. And you can see that we obtained, this model takes into consideration two intermediates on the surface. And we can see here that they both have this exponential decay as a function of potential, but it's just hard to see because we clearly have a very short-lived intermediate and a very long-lived intermediate. And we're also able to obtain, but as we see as a function of potential, the lifetimes of these species decrease. And we can also obtain from this parallel pool model a mole fraction of intermediate A, and we can see that intermediate A, this one that we're accounting for here, is very, very abundant on the surface of the catalyst, regardless of potential. So we can see that this intermediate A is definitely the dominant intermediate in methanol oxidation. So now that we have our coverages and we've quantified our coverages and our lifetimes, we're actually able to obtain a CO2 site time yield. And essentially, which is a turnover frequency, but for a specific product. And we were able to obtain a CO2 site time yield and plot that versus the CO2 partial current density. Now, essentially, what we're doing here is we're plotting two measures of intrinsic activity, this site time yield measurement and this the normalization of the ECSA, and we see the direct correlation between the two independent variables of one another. So this finding that we have here, it really we believe really validates our experimental approach, our experimental ESITCA approach, that these two measures of intrinsic activity correspond very nicely with one another. And then furthermore, we were able to actually obtain pretty interesting data with this site time yield, because now we can actually take we can actually understand the percentage of CO2 that's formed through this intermediate A here, and by using this equation here, and you can see that the dominant, you can see a big dominance of CO2 is obviously dominated by this intermediate A. And this is information that you really wouldn't be able to obtain in any other way other than understanding the coverages and the lifetime simultaneously as a function of potential. So now that we have our data, we can, this is not a technique that's coupled with IR at this moment. So we just need to use literature to understand, to actually identify what these intermediates are, because that's something that we can't accomplish yet. So therefore, we looked into literature, and we see that the low potential methanol oxidation wave, which is this CO2 partial current density, essentially scales really nicely with the integrated band intensities of adsorbed CO. And we see here that this is a intermediate surface coverage of intermediate A, and we can see that at 0.8 volts, we can see that this follows a very similar trend that we see of total coverage, where the lifetimes this is our short-lived intermediate, where we can see our lifetimes are decreasing as a function of potential. So all of these correlations lead us to believe that this intermediate A is potentially linearly bonded CO on the platinum surface. So in conclusion, for our electrochemical Sitka experimentation, we were able to obtain a intermediate coverage and surface lifetimes. And you can see here that the partial current densities, this is the trend of the average partial current density as a function of potential. And you can see here that we get the most partial current density leading toward the production of CO2 at these 0.8 volts, where we have this intermediate, this optimal balance essentially, where we have still a relatively very high coverage, but also a very low lifetime. And we understand that the rate determining step of methanol oxidation is the chemical coupling of CO and surface hydroxide. Therefore, we see that at these lower potentials at 0.6 and 0.7, we're actually lifetime limited just by the how long the intermediates are actually on the surface for, because there isn't a lot of oxygen on the surface. But then at these higher potentials, we see that we're coverage limited, because now the surface is being overpopulated by oxygenated species, and now methanol is not being able to adsorb to active sites. So just very quickly, I just want to go into a brief future work that we're really excited about, because now that we've validated this electrochemical Sitka approach, we actually want to investigate the significance of cations in solution. So it's well known in catalytic literature that cation identity significantly affects the electrocatalytic activity, and these are just some examples of as the cation gets larger, the activity of the partial current density of CO and CO2, the partial current density of CO gets increases, and also the overall current density for CO2 reduction increases as well. And so what we would like to do is to understand and explain the origins of cation identity in electrocatalytic activity. So it's very difficult to actually probe these cations. There's a lot of theories of what these cations are doing in solution that are promoting the activity. There's theories of specific adsorption. There's theories of strengthening the electric field and stabilizing key intermediates that lead towards particular products. But if we do experiments in solutions of different cations, like an isotopic switch in one cation, and then another experiment where we do an isotopic switch in the presence of a different cation, we can compare our coverages and our lifetimes and understand if there's a mix of both that are contributing to this enhancement, or the coverages are going up, or the lifetimes are going down, and so forth. So I just would like to reinstate that Sitka quantitatively measures our coverages and our lifetimes, and this really elucidates electrocatalytic phenomena. And this is a very versatile technique that can really be applied to any reaction that produces a volatile product. It won't necessarily be easy, but it's definitely achievable. And with that, I'd like to acknowledge my advisor, Dr. Clark, for all his guidance and support, and my group members. They're really amazing. And I would really like to thank Teresa Pond. She helped me build my experimental setup, and the Kaufman Foundation for my funding. And I'll take any questions. Thank you so much.